Continuing on with our lecture on chapter 6, let's talk next about a really critical aspect of stoichiometry. And yes, just to reiterate, the next exam will still be next Thursday. That's correct. It'll cover approximately chapter 4 through 7. Maybe chapter 8 if we get to it, but chapter 8 is likely not going to appear on the second exam. So a critical aspect of stoichiometry is this idea of limiting reactants. Some reactions just happen to work best when you have excess reactant. If you have a really valuable pharmaceutical molecule, or if you have a really valuable protein or peptide that you want to modify, you're going to use an excess of a cheap reagent to get the reaction to work effectively. Now, product formation is limited by the moles of each reactant and their stoichiometry. Now, the limiting reactant is formally defined as the reactant that is completely consumed first during a reaction that prevents the reaction from proceeding further. So again, we're going back to food analogies. So a lollipop requires a stick and a piece of candy, right? So if we think about a lollipop, it requires a stick and a piece of candy. So if we're putting together and we're making lollipops from the raw materials, if we have 4 pieces of candy, and we have 6 sticks, how many lollipops can we make? So if we put together our lollipops and our sticks, how many? We can make a total of 4, right? So we can make a total of 4 lollipops. Okay. And how many sticks do we have left over? How many sticks do we have left over? So after we've used up 4 sticks and 4 pieces of candy, we have 2 sticks excess. So our sticks are excess reagent, while our pieces of candy are our limiting reagent. We use up all our candy and we can't make any more lollipops. Okay, one thing to note, we have to consider both the amount of each of our reactants and the stoichiometry. So a lollipop requires 1 stick and 1 piece of candy. It's a 1-to-1 stoichiometry. So now, just to demonstrate that this example actually has relevance to chemistry, I'm going to ask you how many moles of zinc sulfide are produced by reaction of 6 moles of sulfur and 4 moles of zinc. Okay, so looking at this simplified equation, I know that this formula for sulfur has been simplified just so that way we can look at this example and draw analogies to the pictures that we've drawn. So if we have, for zinc, if we have 4 moles of zinc and we have 6 moles of sulfur, and we have a 1-to-1 ratio, how many moles of zinc sulfide can we make? How many moles of zinc sulfide can we make? Just like our lollipop and stick analogy, how many moles of zinc sulfide can we make? 4. We can make 4 moles of zinc sulfide. In addition, we also have 2 moles of excess sulfur. If we wanted to write this in a more procedural manner, so 4 moles of zinc, we know that we have 1 mole of zinc sulfide per every 1 mole of zinc, and that would give us 4 moles of zinc sulfide. Further, yep. Now, to elaborate on this example and to expand on this idea, I really want to make the point that the limiting reactant is not necessarily the reactant with the least number of moles. We have to consider the stoichiometry. So for example, let's suppose a sandwich requires 2 pieces of bread and 1 piece of cheese. Okay, so let's draw a picture of that. So we have 2 bread plus 1 cheese and when we mix those together, we in turn get 1 sandwich. Okay, so then let's try to answer the question, how many sandwiches can we make if we have 4 pieces of bread plus 3 pieces of cheese? How many sandwiches can we make? So let's draw a picture. Let's draw a picture. So what are we going to run out of first? Bread or cheese? So let's pair things out. So if I have 2 pieces of bread, I'm going to use up 1 piece of cheese. If I have another 2 pieces of bread, I'm going to use up my other piece of cheese. Can I make any more sandwiches after this point? Can I make any more sandwiches after this point? No. So how many sandwiches do we make? How many sandwiches do we make? 2, yep. Yep, we can only make 2 sandwiches. So what is our limiting reactant? What ingredient limits the amount of sandwiches we can make? So bread is limiting because we run out of bread and then we can't make any more sandwiches. Cheese is in excess because we have an excess amount of cheese. If we're thinking about this from a stoichiometry perspective, so if we have 4 bread and we have 2 sandwich per bread, if we have 1 sandwich per every 2 bread, if we punch this into our calculator, that in turn gives us 2 sandwich. So we can make a maximum of 2 sandwiches in this process. Does this make sense to everyone? Does this idea that limiting reactants are based on stoichiometry? We have to consider our stoichiometric ratio. It's not just the smallest number of moles. It's the reagent that is consumed first based on the stoichiometry. Okay, so let's continue on with this idea and let's try to apply this to a reaction. So how many moles of tin 4-chloride are produced by the reaction of 4 moles of chlorine and 3 moles of tin? Keeping in mind our reaction looks like this. So tin solid plus 2 chlorine molecules leads to tin tetrachloride or tin 4-chloride. And we can already see the parallels between our bread and cheese example. If we have 3 moles of tin, whoops, let me reverse the colors a little bit. Let me reverse the colors just so that way it's a little easier for us to see what's going on. So we have 2 chlorine and we have 4 moles of chlorine plus tin solid, and we have 3 moles of tin. How many molecules of tin 4-chloride can we make? How many molecules of tin 4 chloride can we make? Recalling our bread and cheese example, thinking about chlorine as our bread, as it has a 1 to 2 stoichiometry with our product. How many moles of tin 4 chloride can we make by analogy? How many moles of tin 4 chloride can we make? And don't be shy to share your responses in the chat or verbally. So it would be 1 if we started with 2 moles of chlorine, but since we have 4 moles of chlorine, how many moles of tin tetrachloride can we make? How many moles of tin tetrachloride? We can make 2. Just like our sandwich example. So to show this using stoichiometry, if we start with 4 moles of chlorine, we get 1 mole of tin tetrachloride for every 2 moles of chlorine. That gives us 2 moles of tin tetrachloride. If we repeated the same calculation for our tin, if we have 3 moles of tin, we have 1 mole of tin tetrachloride per 1 mole of tin, and that would give us an expected 3 moles of tin tetrachloride. However, the rule when you're dealing with chemical reactions is that the smallest amount of product produced is produced from your limiting reactant. And you cannot produce more product than that produced from your limiting reactant. We don't have enough chlorine to react all of our tin. It's just like trying to make a sandwich when you've run out of bread. You can't proceed your reaction any further. So we would expect 2 moles of tin tetrachloride to be produced from this reaction. Does that example make sense to everyone? Does everyone see the link between stoichiometry, which we've talked about earlier, and this idea of limiting reactants, where the limiting reactant is the reactant that is consumed first based on your stoichiometry and produces the least amount of product? Can I get some confirmation in the chat that everyone's comfortable with this idea? If not, if I can get some questions in the chat, if anyone's unsure about any aspect of this problem, really don't be shy to ask. Is everyone okay so far with this idea? Okay. Let's do some practice then. So what I'm going to show you now is a procedural way of identifying the limiting reactant. And this method is known as the product method. So to showcase this idea of the product method, first and foremost, we're going to look at our chemical equation. And before we do anything, do we have a workable chemical equation? Can we use this chemical equation with no issues? Are we good to go? Is this equation all set for us to use? No, it's not balanced. So looking, we have 2 iodines on the left. We have 3 iodines on the right. So I'm going to use the least common multiple method. I'm going to cross my number of atoms into the reaction coefficient. So I have 3 iodine and 2 nitrogen triiodide. And that in turn gives us the following balanced chemical equation. However you balance your chemical equation, that's solely up to you. There are many methods. Now, what we're going to do is we're going to try and calculate the moles of nitrogen triiodide produced by reaction of 2 moles of nitrogen and 2.5 moles of iodine. Now remember, we can't just look at the absolute number of moles and say one is limiting. We have to consider the stoichiometry. I can't stress this enough. You have to consider the stoichiometry. So, first and foremost, in terms of so here's what's requested from us in this problem. We want to calculate the moles of nitrogen triiodide produced, and we want to calculate the moles of excess reactant left over. Okay, so in terms of our step-by-step guide, first we need to calculate the moles of each reactant. So we're given that. We have 2.0 moles of nitrogen and 2.5 moles of iodine. Okay, so we have that so far. In later problems, you may have to calculate the moles from mass or something else. Okay, now we have to calculate the expected moles of product generated by complete reaction of each reactant using the chemical equation stoichiometry. Okay, so in the first case, we're going to go from moles of nitrogen to moles of nitrogen triiodide. Okay, that's an easy conversion. If we have 2.0 moles of nitrogen, looking at our stoichiometry, how many moles of nitrogen triiodide do we make per mole of nitrogen? What is our mole to mole ratio? What is our mole to mole ratio? What is our mole to mole ratio? 2 to 1. We have 2 moles of nitrogen triiodide for every 1 mole of nitrogen. So that gives us an expected 4.0 moles of nitrogen triiodide. Okay, let's look at our other reactant, which is iodine. So we're going to go from moles of iodine to moles of nitrogen triiodide. Allow me one moment just to reset OneNote, as it's experiencing a little bit of delay through Zoom, just so that way the sharing is a little more smooth. Okay, so just as a refresher as to what are we doing right now? Well, we are trying to calculate the expected amount of product generated from complete reaction of both of our reactants. So we did our first calculation saying, how much product would I get if I used up all of my nitrogen? Now we're going to calculate how much product are we going to get if we use up all of our iodine. And considering we have 2.5 moles of iodine, we have a lot of iodine, so we should have no problem. Now, this is a very, very important issue that we need to talk about. Looking at our stoichiometry, how many moles of nitrogen triiodide do we make per mole of iodine? So looking at our chemical equation, what is our mole to mole ratio of nitrogen triiodide to iodine? What's our mole to mole ratio? Two to 3, yep. So in turn, if we punch that into our calculator, we have 1.67 moles of nitrogen triiodide expected from iodine. Okay, so now, as a rule, once we have the moles of product expected, in general, as our rule, the reactant that produces the least product is the limiting reactant. So which of these two numbers is smaller? 4 moles of iodine produced from nitrogen, or 1.6 moles of nitrogen triiodide produced from iodine? Which one's smaller, 4 moles of nitrogen triiodide or 1.67? In other words, what is limiting, nitrogen or iodine? Which species is limiting? Which reactant makes the least amount of product? Iodine, exactly right. Iodine is limiting because it makes the least amount of product when completely consumed. Okay, so now that we have this information, we're going to calculate. So we already have the amount of product. So we're making this many moles of nitrogen triiodide. Now what we're going to do is we're going to calculate the amount of each reactant consumed in the chemical reaction using the moles of product produced from the limiting reactant and the chemical equation stoichiometry. So we know that if we have 2.0 moles of nitrogen and 2.5 moles of iodine, that we ended up making 1.67 moles of nitrogen triiodide. Our chemical equation stoichiometry looks like this. Now, to calculate the amount of excess reactant left over, what we're going to do is we're going to take our moles of excess reactant, which is nitrogen, and we are going to subtract the moles of limiting reactant, or the moles of product produced, in this case 1.67 moles of nitrogen triiodide, and we're going to convert our moles of nitrogen triiodide into moles of nitrogen, into the moles of our excess reactant. So we know how many moles of nitrogen do we need to produce how many moles of nitrogen triiodide? What's our mole-to-mole ratio between nitrogen and nitrogen triiodide? How much nitrogen are we using up to make this 1.67 moles of nitrogen triiodide? What's that mole-to-mole ratio? 1 to 2, exactly. So, to calculate the amount of excess reactant remaining, you take the moles of your excess reactant, you subtract the moles of product that you convert into the moles of excess reactant consumed. So if we punch that into our calculator, we'd have 2 minus 1.67 times 1/2, which in turn gives us 1.165, which we round to 1.2 moles of nitrogen remaining. So this is the number of moles of excess. This is our excess. Does this idea make sense to everyone so far? Does the product method make sense to everyone so far? So just as a refresher, we calculate the moles of product expected from each of our reactants. Then we subtract the moles of our product from the moles of our excess reactant after converting our moles of product into the moles of excess reactant. The amount of excess reactant remaining is shown here. Any questions on this example? Any questions on this example? If not, let's try to apply what we've learned to the following example. So we're given the following chemical equation. I'd like you to calculate the moles of silicon tetrahydride produced by the reaction of 3 moles of silicon and 3 moles of hydrogen. And then I'd like you to calculate the moles of excess reactant. So we'll spend about 5 to 6 minutes on this problem. First and foremost, we'll focus on writing a balanced chemical equation. We'll discuss that in about 1.5 to 2 minutes. And then, once we have our balanced equation, I'd like you to calculate the expected moles of product and the moles of excess reactant remaining. And we'll discuss this example first in about another 1.5 to 2 minutes, and then another 5 minutes for our complete solution. And don't be shy to submit questions or responses in the chat or via Canvas. We already see a few responses in Canvas so far. Let's try to get a few more responses and we'll discuss momentarily. And looking at balancing the equation. So this one's pretty straightforward. We have 4 hydrogens on the right. We have 2 hydrogens on the left. So what coefficient do we need? What coefficient do we need to balance hydrogen? We just need to put a 2 in front of hydrogen on the left. So now that we have our balanced equation, let's take another 4 minutes and let's try to solve the remainder of this problem. And the responses I see in the chat so far look quite good. And we'll discuss this example in about another 4 minutes. Don't be shy to submit your responses via Canvas or in the chat. And the responses I see so far via Canvas look encouraging. Let's try to get a few more responses just so that way I can be sure that the entirety of the class is comfortable with this material and allows me to structure my feedback. And the responses I see in the chat look great so far. We'll discuss in about another 3 minutes. And checking Canvas, I see a reasonable pool of responses so far. So let's discuss this example now. So first and foremost, let's use the product method. So let's start by converting from moles of silicon to moles of silicon tetrahydride. If we have 3.0 moles of silicon, we know that we have 1 mole of silicon tetrahydride per every 1 mole of silicon, which gives us 3 moles of silicon tetrahydride. Let's do the same calculation, this time from the moles of hydrogen to the moles of silicon tetrahydride. So we have 3.0 moles of hydrogen times 1 mole of hydrogen, 1 mole of silicon tetrahydride per every 2 moles of hydrogen. That in turn gives us 1.5 moles of silicon tetrahydride. So we see that that is the maximum amount of product produced, and that hydrogen gas is our limiting reactant. Okay, so now that we have our limiting reactant established, let's calculate the mass of, or the moles of excess reactant remaining. So we have 3.0 moles of silicon. We are then going to subtract 1.5 moles of silicon tetrahydride, that's how much product we generate, times 1 mole of silicon for every 1 mole of silicon tetrahydride, which in turn gives us, at the end of our calculation, 1.5 moles of silicon in excess. Does this example make sense to everyone so far? Is everyone comfortable with this idea after practicing the calculations? Let's continue on with this practice and let's do a few more examples. So let's do a guided example here where we're given a word equation, okay? So calcium hydroxide is reacted with nitric acid to yield calcium nitrate and water. Okay, so writing formulas from the name, calcium hydroxide, we have calcium 2 plus, OH minus, that gives us CaOH2. Nitric acid is derived from nitrate, which gives us HNO3. Calcium nitrate, we have calcium 2 plus, NO3 minus. We cross our charges, that gives us CaNO3 and water is just H2O. So looking at this equation, we notice that nitrate is not balanced. We have 2 nitrates on the right, so we need 2 nitrates on the left. On the left, we have 4 hydrogens total. We have 2 hydrogens in water. 2 times what would give us 4 hydrogens? 2 times what would give us 4? What coefficient do we guess for water? 2, yep. Okay, so we have our complete balanced equation. So now we're ready to apply stoichiometry. So we're going to convert from the moles of calcium hydroxide to the moles of calcium nitrate first. Since we're asked to figure out the moles of product, so we take 3 moles of calcium hydroxide times 1 mole of calcium nitrate per every 1 mole of calcium hydroxide. And that in turn gives us 3 moles of calcium nitrate. Let's repeat with another reactant. This time we're going to go from the moles of nitric acid to the moles of calcium nitrate. So if we have, looking at the problem, we have 4 moles of nitric acid. We know that we have 1 mole of calcium nitrate. And how many moles of nitric acid are required? How many moles of nitric acid are required? Just looking at the chat, for every 1 mole of calcium nitrate, we have how many moles of nitric acid required? Looking at the chat, I see 2 moles of nitric acid required. So that would give us a predicted moles of product of 2 moles of calcium nitrate. So then we put a box around nitric acid. So our nitric acid is limiting. So we end up making 2 moles of calcium nitrate. To calculate the moles of excess reactant remaining, if we have 3 moles of calcium hydroxide, we're then going to subtract our 2 moles of calcium nitrate. However, we have to convert back to the moles of excess reactant. So we have 1 mole of calcium hydroxide consumed for every 1 mole of calcium nitrate. And if we punch that into the calculator, that gives us 1 mole of calcium hydroxide excess left over. Does that make sense to everyone so far? Any questions so far on this example? Okay, so let's keep going with this problem set. And let's try to work on the following example, where we're looking at the reaction between magnesium and aluminum chloride. I'd like you to calculate the moles of magnesium chloride when 2.5 moles of magnesium metal and 2 moles of aluminum chloride react. And then I'd like you to calculate the moles of remaining reactants. So let's spend about 2 to 3 minutes writing a balanced chemical equation, and then another, for a total of 5 to 6 minutes, solving the remainder of this problem. And don't be shy to submit your responses via Canvas quiz 6.8.1. And if you have any questions, or if you'd like me to provide individualized feedback, don't be shy to submit a public or private message via the Zoom chat. And we'll discuss the balanced equation in about 2 to 3 minutes. And we'll discuss the balanced equation in about another 1.5 to 2 minutes. And the message proposed balance coefficients look good so far. So let's discuss this example. So first and foremost, magnesium metal. So we have magnesium solid, aluminum chloride. So we have aluminum 3 plus and Cl minus. We cross our charges. That gives us AlCl3. That in turn yields magnesium chloride, which again, if we have magnesium 2 plus Cl minus, we cross the charges. That gives us MgCl2 and aluminum metal, which is Al solid. So looking at this equation, it's not balanced. We're going to use the least common multiple method for chlorine. And that in turn gives us 2 aluminum chloride, 3 magnesium chloride. We balance magnesium and aluminum by adjusting our coefficients. So now we have our balanced chemical equation. So I'd like everyone to take about another 4 minutes and work through this example and calculate the expected moles of product generated and the moles of excess reactant remaining. And we'll discuss this example in about 4 minutes. And the responses I see in the chat and via Canvas look perfect so far. Let's try to get a few more responses. I want to make sure the majority of the class is engaging and comfortable with the material, and then we'll discuss momentarily. And for the response I see in the chat, I would just double check that when you calculate the moles of excess reactant remaining, you remember to convert the moles of product into the moles of excess reactant consumed using the stoichiometry. And we'll discuss the solution to this problem in about another 2 minutes. So checking Canvas, we have a reasonable pool of responses. Let's give everyone another minute to minute and a half. Let's try to get a few more responses, and then we'll discuss. Okay, we have a reasonable pool of responses via Canvas. The majority of the class is submitting responses via Canvas or in the chat. So let's discuss this example. So we're asked to figure out the moles of magnesium chloride formed. So we're going to convert from moles of magnesium to moles of magnesium chloride. We know if we have 2.5 moles of magnesium, that we generate 1 mole of magnesium chloride for every 1 mole of magnesium, which in turn gives us 2.5 moles of magnesium chloride. Next, we have 2 moles of aluminum, and we're going to convert the moles of aluminum into moles of magnesium chloride expected. So if we have 2.0 moles of aluminum, and we know that we have, what's our mole to mole ratio? How many moles of magnesium chloride do we make per mole of aluminum? What's our mole to mole ratio of magnesium chloride to aluminum? What is our mole to mole ratio? What's the mole to mole ratio of magnesium chloride to aluminum?
3 to 2.
3 to 2, exactly right, which would give us an expected amount of 3.0 moles of magnesium chloride. Ergo, magnesium is limiting, and we only generate 2.5 moles of magnesium chloride. Continuing on, the moles of aluminum in excess is equal to our moles of aluminum, which is 2.0 moles of aluminum, minus 2.5 moles of magnesium chloride. And now, looking at it, how many moles of aluminum do we need to react to generate per mole of magnesium chloride? What's our mole to mole ratio of aluminum to magnesium chloride? What's our mole to mole ratio of aluminum to magnesium chloride? What is our mole to mole ratio? And don't be shy to type it in the chat. 1 to 3? 2 to 3, yep, perfect. So that gives us for our moles of aluminum in excess, that gives us 2 minus 2.5 times 2 over 3, which gives us 0.33 moles of aluminum in excess. And don't worry, I'll fix that small glitch in the Canvas quiz, just so that way when we go back and review this example, we'll have all the responses match our lecture responses. Any questions on this example? Any questions on this example 6.8.1? Again, make sure you're using the correct stoichiometric ratio when you're calculating your excess reactant. Any questions on this example? And remember, you can reattempt any of these problem session problems via Canvas. Everything is there on Canvas. So that way, if you want to retest your familiarity and understanding of the lecture material, that's all available to you. Any other questions on this example? Does the logic behind this make sense so far? Okay, so let's keep going with this problem. So I provided just some additional space in case we needed it. We didn't, so we'll skip past this. Now, I'm going to teach you a method now called the ICE method. And you may be thinking to yourself, a lot of students when they see this method think to themselves, well, this seems very roundabout. It doesn't seem as useful as the other methods. I am going to say that if you're planning on taking Chem 102 or the second general chemistry course, at least learning how the ICE method functions is invaluable because you'll be making ICE tables a lot in general chemistry too. So let's talk about the ICE method, and let's do that in the context of a problem. So here we're asked how many grams of iron 3 sulfide can form when we have 64 grams of hydrosulfuric acid and 180 grams of iron 3 chloride reacting according to the following equation. So first things first, in the ICE method, you're going to need an ICE table. We'll see that below. First, we're going to calculate the moles of each reactant. So if we have 64.0 grams of hydrogen sulfide, we know in 1 mole of hydrogen sulfide, we have 34 grams. Just to check before we move on, is everyone comfortable with these molar mass calculations? If anyone wants me to show a molar mass calculation for any of these future problems, don't be shy to ask. We've done these molar mass calculations so many times that you should start being able to, in your calculator, compute out the molar mass and enter it in to your line-by-line conversion without too many steps. Let's repeat the same process and let's calculate the moles of iron 3 chloride. So in 1 mole of iron 3 chloride, we in turn have 180 over 58.5. One moment, that gives us a molar mass of 164.8 grams. Punching that into our calculator, we get 0.0289 moles of iron 3 chloride. Okay, and now that we have this established, what we're going to do is in our reactant side, we're going to put our reactant. So this is H2S plus FeCl3 leads to, and now we list our products, which is Fe2S3 and HCl. Some metal complexes, such as iron 3 chloride, are considered quote-unquote acidic metal complexes because they're able to react with weak acids to generate solutions of strong acids. Now we're going to copy and paste our coefficients. So we're going to put the 3 in front of H2S, the 2 in front of iron 3 chloride, and the 6 in front of HCl. Okay? Now what we're going to do, you notice there's a column. There's a column for each of our reactants and products and a row titled initial moles. It's abbreviated I. This is the initial moles of each of our reactants. And we're going to plug that in. We're going to plug each of our calculated moles into our initial moles. Let me double check the moles of iron 3 chloride. I think there was a calculator error. There was. If we punch that into the calculator, we should get 1.092 moles of iron 3 chloride. So we're going to plug both of our calculated moles of each reactant into our initial moles column. Then what we're going to do for our products, our initial moles will be 0. We don't have any product at the beginning of our reaction. Okay, so this is what your ice table should look like after the first step. When we've calculated the moles of each reactant, and then we've placed the moles of each reactant and the moles of each product into our ice table in the initial column. Does this make sense to everyone so far? Does this make sense to everyone so far? Okay, so now what we're going to do in our ice table, let's zoom out just a little bit. So in our ice table, the reaction is going to progress a certain amount that we call the reaction progress X. We will consume reaction coefficient times X moles of each reactant, and we will produce the reaction coefficient times X moles of product. All of this change coefficient expression is based on the chemical equation reaction coefficients. Okay, so how does this work in practice? Well, let's rewrite our ice table. Let's rewrite our ice table. And let's just copy over our moles. Okay, perfect. So now that we have our ice table copied over, let's look at the next steps in our procedure. So we're going to place negative reaction coefficient times X in the change row for each reactant. And we're going to place positive reaction coefficient times X in the change row for each product. Okay? Then what we're going to do is we're going to add together the initial and change columns of the ice table for each reactant and product to give an expression for the final moles of each reactant and product. So initial plus change is equal to final. So let's show what that looks like. So the change coefficient for each of our reactants will be negative reaction coefficient times X. So what would the change coefficient be for H2S? What would the change coefficient be for hydrosulfuric acid? What would the change coefficient be? So it would be minus what times X? Minus what times X? All we're doing is reading off our reaction coefficient. So what would our change coefficient be? What is the reaction coefficient for hydrogen sulfide? What is the reaction coefficient for H2S? What's the number in front of H2S in our equation? 3, exactly right. So this would be minus 3x. Okay, what would the change coefficient be for iron 3 chloride? It would be minus what times x? It would be minus what times x? What's the coefficient in front of iron 3 chloride? Minus 2x, exactly right. For iron 3 sulfide, it would be plus what times x? What's the coefficient for iron 3 sulfide? What is our coefficient? 1, yeah. And for hydrochloric acid, it'll be plus what times X? It'll be plus what times X? What's the coefficient for hydrochloric acid?
6.
Yep, exactly. Now, the beautiful thing about an ice table, and the reason why it's so useful, is that if a reactant is limiting, the final moles of reactant should be 0, right? So what you're going to do is you're going to set the final moles equal to 0 for each reactant. So you're going to have initial plus change is equal to 0. And you'll often end up with expressions that look like initial minus coefficient times X is equal to 0. Okay? So we're going to put as a preliminary rule a 0 for each of our final moles of reactant. So we'd end up with an expression of 1.822 minus 3x is equal to 0, and 1.092 minus 2x is equal to 0. Now the key feature of this idea in an ice table is that only one value of x is correct. So what we're going to do, now that we have this ice table set up for our reactants, is we are going to solve for x. And there's a beautiful shortcut. A shortcut that you can use, and this is one thing that if we delve into the ice table method, this is what we can take from this method that I like to use a lot. You can divide the initial moles of each reactant by that reactant's reaction coefficient, and that gives you X. So for example, looking at our 1.822 minus 3x is equal to 0, this is our hydrosulfuric acid expression. X is equal to 1.822 over 3. Which gives us 0.607. Okay, that's one of our values of X. Let's look at our other value of X, this time for iron 3 chloride. In this case, X would be equal to 1.092 over 2. And if we solve this expression, we get a value of X of 0.545. Now, just like before, as the limiting reactant makes the least amount of product, the smaller value of X is the limiting reactant. So what is our limiting reactant? Is it H2S or FeCl3? Is it hydrosulfuric acid or iron 3 chloride? So what is our limiting reactant? Which reactant in the ice table has the smaller value of X? Which reactant has the smaller value of X? Which reactant has the smaller value of X? Just as a side-by-side comparison. Hydrosulfuric acid or iron 3 chloride? Which value of X is smaller? Which value of X is smaller? For iron 3 chloride, yep. So what we can say is that iron 3 chloride is limiting. And we are going to use this value of X in our ICE table to calculate the final moles of each reactant and product. So let's show how this would work. So first and foremost, our initial moles of hydrogen sulfide are 1.822. We're going to subtract 3 times X. In this case, X is 0.545. And that in turn gives us a final moles of 0.245 moles of H2S. So we've almost instantaneously calculated the moles of excess reactant. For iron 3 chloride, we have 1.092 moles. So minus 3 times 0.545. Let's enter that into our calculator. Oh, it's not 3. It would be minus 2 because our coefficient is 2. So 2 times 0.545. And that in turn gives us a value of 0, which makes sense because iron 3 chloride is limiting. Now looking at our product, our change coefficient for iron 3 sulfide is plus X, so we'd add 0.545, which gives us 0.545 moles of product. For HCl, it's plus 6X, so 6 times 0.545, and that in turn gives us 3.28 moles of HCl. So the real utility of the ICE method is it allows us to very quickly identify the limiting reactant, and it allows us to calculate the moles of each species in our chemical reaction all at once. Does that make sense to everyone so far? Does everyone understand the logic behind the ICE table method so far? Let's do one more recap. Let's do one recap from start to finish. Okay, so in the ICE method, we calculate the moles of each of our reactants. Once we have the moles of each of our reactants, then we plug them into the initial column. Then we substitute into our ICE table the reaction coefficient times X for the change row. So our coefficient is 3 for H2S, so we have a 3. Our coefficient is 2 for iron 3 chloride, so we have a 2. We subtract our coefficient times X for our reactants. We add our coefficient times X for our products. Now, if one of our reactants is limiting, the final moles will be 0. We'll use up all of our limiting reactant. So we have 2 expressions for X that we're going to solve for, and the smaller value of X is limiting. So we're going to solve for X by dividing our moles by our coefficient. The smaller value of X is limiting, and we're going to plug that value of X into our ICE table to calculate the amount of each of our reactants and products. As we can see, iron 3 chloride is limiting because we've used up all of our iron 3 chloride. Hydrosulfuric acid, H2S, is in excess because we still have excess reactant remaining. if we wanted to take this further and we wanted to go from the moles of iron 3 sulfide to the grams of iron 3 sulfide, all we would have to do is use the molar mass. In this case, we have 55.8 times 2 plus 32 times 3. So starting with 0.545 moles of iron 3 sulfide, we know that we have 207.6 grams per every 1 mole of iron 3 sulfide. Which in turn gives us 113 grams of iron 3 sulfide. Any questions on this example? Any questions on this example? I know it seems very steppy, but the ICE method is very quick when you have to calculate the moles of product and the moles of excess reactant. It's invaluable if you have to calculate the quantities of multiple species in your chemical reaction at once. So can I get some responses in the chat? Does everyone understand how the ICE method functions and how it can be used to solve limiting reactant problems? Is everyone comfortable with this idea so far? So to test our understanding of this idea, of this concept of the ICE method, I'd like you to take a look at the following problem. So you're asked to calculate how many grams of iron, So you're asked to calculate how many grams of iron 3 sulfide can form. This is just an excess space that we have for problem solving set from the previous example. Let's move on to a new example. And you can submit your responses in Canvas quiz 6.8.3. I'd like you to calculate how many grams of nitrogen monoxide can form when 30 grams of ammonia and 40 grams of oxygen react according to the following equation. And I've provided you an ICE table below if you wish to use that. So don't be shy to submit your questions and responses in the chat or via Canvas. And I'll be checking Canvas in the chat throughout, and we'll discuss this example in about 6 to 7 minutes. But again, don't be shy to submit any of your proposed questions. And we already have some responses via Canvas. Let's try to get a few more responses and we'll discuss in another 5 minutes. And if you have any questions at all, don't hesitate to ask them in the chat, verbally, or via Canvas. And don't be shy to submit your proposed responses via Canvas or in the chat as a public or private message so we can discuss as a class. And we'll discuss this example in about another 4 minutes. And I would double check to make sure that you've accounted for which reactant is limiting and the reaction stoichiometry. And we'll discuss this example in about another 3 minutes. And so far, the responses I see in Canvas look quite good. Let's try to get a few more responses, and we'll discuss in about another 2 minutes. And the responses I see in the chat look great so far. And we'll discuss this example in another minute. Let's try to submit a few more responses via Canvas in the chat, just so that way I can provide some individualized feedback. And if there are any questions working through these problems, again, don't hesitate to ask. Okay, so let's discuss this example. So first and foremost, we need to calculate the moles. So if we have 30.0 grams of ammonia, we know that in 1 mole of ammonia, we have 17 grams. So punching that into our calculator, that gives us 1.76 moles of ammonia. Okay, if we have 40.0 grams of oxygen, we know in 1 mole of oxygen O2, we have 32 grams. Remember, when we say oxygen in the context of a chemical reaction, it's referring to molecular oxygen. So punching that into our calculator, we get 1.25 moles of oxygen. So punching this in, let's plug in our initial moles into our ICE table. Okay, now let's plug in our change coefficient, which is minus our reaction coefficient, which is 4 times X. What would the change coefficient for oxygen be? What would the change coefficient for oxygen be if we're using the ICE method? What is the change coefficient for oxygen? It would be minus 5x, okay? For nitrogen monoxide, it's plus 4x. For water, it's plus 6x. So now that we have this set up, what we're going to do is we're going to solve for x. So the x for ammonia in this case is 1.76 over 4. Punching that into our calculator, we get 0.44. Okay. For oxygen, our value of x is 1.25 over 5. And that gives us 0.25. So I'd like you to tell me, with this information in hand, which reactant is limiting? Which reactant has the smaller value of x? Which reactant has the smaller value of x? Which reactant is limiting? Which reactant has the smaller value of x, the smaller reaction progress value?
Oxygen?
Yep, oxygen, exactly right. So oxygen with its value of x of 0.25 is limiting. So oxygen is limiting, and what we're gonna do is we're gonna plug in our value of x from our limiting reactant. So that in turn, if we punch that into our calculator, gives us 0.76 moles of ammonia remaining, 0 moles of oxygen remaining, and 1.0 moles of nitrogen monoxide remaining, and 1.5 moles of water produced. Now that we have our moles of each chemical species calculated pretty quickly, we're going to take our 1.0 moles of nitrogen monoxide and convert it into grams. Considering we have 30 grams in 1 mole of nitrogen monoxide, that gives us 30 grams of nitrogen monoxide. And there we go. So, what's everyone's opinion of the ICE method? Do you like it? Do you not like it? Some students really like the ICE method. Other students prefer the product method. I think the ICE method, it's slow, but if you're practiced with it, it's very organized and it makes it very easy to go back and check your work. If you don't want to use the ICE method, you're more than welcome to use the product method. This is just another tool at your disposal for handling limiting reactant and stoichiometry problems. I'd say the ICE method is best suited when you have a reaction where you want to quickly calculate the moles of each species in your chemical equation. So any questions on this example? Any questions on this example? So, definitely, a lot of these examples, you want to practice a fair number of limiting reactant problems to really get familiar with it. I just left some extra space. So we're at a point now where we're going to take and we're going to cover the remaining portion of this chapter in lecture on Monday. So we're at a great stopping point. We covered the ICE method. We applied the ICE method. Now you have multiple methods at your disposal. And what we're going to do now, what I'd like you to do over the weekend first is prepare for the thermochemistry laboratory, making sure you have the materials. We'll do that next week once we lecture on thermochemistry. I'd like you to catch up on the lab reports and quizzes that are due this week. Just because I know Saturday is a holiday, so I want to make sure everyone can catch up with the quizzes that are due Monday. And then I'd like you to attempt some problems in the problem solving set on stoichiometry. And I'll also be posting later today the quizzes that will not be due this week, but next week. So that way, if you're feeling adventurous and want to practice some stoichiometry and balancing equation problems in a context similar to the exam, it will all be available for you to practice. Now, in terms of the exam, let me just pause this recording.